Hello everyone, I'm Ziyulin from Fuzhou University. I'm very happy to represent Tuoli, Jia-Ju and others to share the paper about race condition in OS kernels. Generally, a data race occurs in concurrent programming when two or more threads access the same memory location concurrently, and at least one of the sets is a write operation. Some data races are harmful since they can cause dangerous issues such as data corruption, unified behavior, and source leakage. First, the code logic of the operating system is quite intricate. Second, OS kernels are highly concurrent, and the concurrent execution of the OS code is quite complex. Third, OS kernel improve very complex serialization such as mutex lock, semaphores, and so on. Developers can use error serialization mechanism by mistake. However, data race in an OS kernel can cause serious security issues such as DOS attack, privilege escalation, and restriction bypassing. For example, dirty call is a dangerous vulnerability caused a data race in the memory management subsystem of the Linux kernel. By exploiting dirty call, the attacker can maliciously corrupt critical memory and even obtain root privilege. So in data race detection, a locking rule indicates which variable should be protected by which lock, and data race can be identified by checking whether a given variable access violates any locking rules. The figure shows an example of locking rules. The annotation from the kernel developer shows the locking rule that DYN list should be protected by DYN lock. However, detecting data race in OS kernel has three main challenges. First, as introduced above, data race detection can be carried out by checking whether a given variable access violates any locking rules. However, on the one hand, operating systems have insufficient documents about which variable should be protected by which lock, and thus it's impossible to obtain locking rules from the document directly. On the other hand, a variable and the lock to protect it exists in the same data structure in many cases, but it's difficult to identify whether a variable and the lock are from the same data structure due to complex layer caused by structure nesting. Therefore, deriving locking rules from the code directly is not feasible. Second, in the kernel code, due to the heavy use of pointers and the data structures, the alias relations between variables can be very complex, which can significantly affect the effectiveness of the detections of locking rule violation. Finally, some data races are benign and cannot cause security issues, and at least identifying harmful data race is necessary. However, identifying harmful data races automatically is difficult because the code base of OS kernel is very large and the logic of kernel code is very complex. So to address the above challenges, we propose three key techniques. First is field-aware mining method to deduce locking rules. Second, alias-aware checking method to check locking rule violation. Third, a pattern-based estimation strategy to identify harmful data races. We first introduced our field graph, which is used to identify whether a variable and a lock are from the same data structure. In the field graph, each node represents a field and each edge represents how a lower layer field is accessed from a higher layer structure. Fields represented by nodes that have the same ancestor are from the same data structure. A field graph is updated by handling each arrow operator and do not operate, which can present failed access operations. For each such operator, we insert an edge labeled with the accessed field from the node representing the base structure and the node representing the accessed field. Here is a simplified example abstract from the EXYNOS4 is driver code. Take the statement in the line 3 as an example. The field dev private is accessed through an arrow operator and accessed to FIMC. And layers we insert an edge labeled with developer from the node N1 to node N2. After handling all the field access, the final field graph is as the figure shows. In the field graph, the node presenting CTX namely N5 and the node representing log name N4 have a common ancestor namely N2, and layers they can be deduced from the same data structure from the field graph. Given a variable V and a local L, they are from the same data structure identified by the field graph. Let NP be the number of access to V that is protected by L, and NA be the number of all access to V. At least one access is a write operation. If the equivalent of NP and NA is larger than a given threshold T, all access to the variable V should be protected by the log L. OS kernels are large code base with complicated lines relations using our field graph. Whether two variables are aliases can be identified by checking whether the two variables existing in the same nodes in the field graph. After identifying alias relationships, we employ a log set analysis to detect data races. Specifically, if a log is acquired, we insert a node representing the log into the log set. If a log is released, we remove the node representing the log from the log set. When the variable V is accessed, for each locking rule, such as VL, if V is accessed while the node representing L is not in the log set, a data race is identified. In the example, suppose the let FIMC arrow, VID cap arrow, CTX should be protected by FIMC arrow lock. The log FIMC arrow lock is removed at 11.7 from the log set, but CTX is accessed at line 8. Since CTX and FIMC arrow, VID cap arrow, CTX are aliases, a data race is identified. We have actually 4 patterns that can cause security problem at present. First, if a receive variable is a pointer that is assigned or checked by null, a null pointer dereference can occur. Second, if a receive variable affected a bench check of error handling, an error handling bypass can occur. Thirdly, if a receive variable affected multiple branches, undefined behavior can occur. First, if a receive variable is checked before being used but list check and use are not protected by a common lock, a double fetch can occur. Based on the 3 key technique, we present a total automatic framework to detect data race in OS kernel. It's intricate the 3 key techniques introduced and report harmful data races. The figure shows its architecture. We have evaluated LR miner in Linux and FreeBSD, and the information of these 2 operating systems is shown in the table. The table shows the evaluation result of LR miner. LR miner totally represent 200 harmful databases, among which 37 are no pointer dereference, 65 are error handling bypassing, 60 undefined behavior, and 38 are double fetch. The result shows that LR miner can detect harmful databases effectively. We have also compared three other tools to detect databases. The results show that LR miner can find more databases with few false positives. At least, we make a conclusion of our paper. Detection of databases in OS kernel is complex. We developed a novel method named LR miner to effectively detect databases in OS kernel. It used three key techniques: a field-aware mining method to deduce locking rules, alias-aware checking method to check locking rules violation, a pattern-based estimation strategy to identify harmful databases. We have evaluated LR miner on Linux and FreeBSD and found 200 harmful databases. We also compare LR miner to three well-known tools to detect databases, and it outperformed these tools. That's all. Thanks for listening. If you have any questions, please contact the first author of this paper. His name is Tuoli.